Observations on the yield of a chemical reaction taken at various temperatures were recorded as follows. So we have the temperatures and the X there, then the yield, the percentage, the Y. In this tutorial, I'm going to fit a simple linear regression model of the form yi is equals to beta naught plus beta 1 xi plus ei, where the ei there is the random error term. I'll then go on and construct an ANOVA table and test for the significance of the regression using alpha equals to 0.05. Lastly, I'll test the hypothesis that H naught, beta naught is equals to 0 versus the alternative, beta naught is not equal to 0 at alpha equals to 0.05. So given that data there, to fit a linear regression model of the form yi equals to beta naught plus beta 1 xi plus the random term ei there, we have to estimate the slope of the beta 1. So the estimate of the slope, the beta 1, we'll call it beta 1 hat. And the formula for beta 1 hat is equals to summation of xy minus n times x bar times y bar divided by the summation of x squared minus n times x bar squared, which we'll write in short as sxy divided by sxx. For the estimate of beta naught, we denote it by beta naught hat, and it's given by y bar minus beta 1 hat times x bar. These formulas for beta 1 hat and beta naught, we can find them in the formula booklet which will be given in the tests or for exams. So these formulas will be given. So what is needed is to calculate the following values. And to calculate those values, the summation of xy, the x bar, the y bar, the summation of x squared. What you need to do is you need to have a calculator which has a statistics mode. And from that calculator which has a statistics mode, if you enter your variables, the x and the y there, you will then get the summation of x from the calculator. And the summation of x would have it as 2,700. The summation of x squared is 645,000. And the summation of xy is 237,875. And the summation of y is 1037.8. So we now have those values, and we note that the number of observations in this case, our n, is at 12. So we have our n equals 12, and we can calculate our x bar. X bar is the summation of x divided by n. So in this case, it will be 2,700 divided by 12. Our y bar is the summation of y divided by our n, which gives us 1037.8 divided by 12. So we now go on and write our sxy. Our sxy, we are saying, is the summation of xy minus n times x bar times y bar. So substituting the values of the summation of xy, the n, the x bar, and the y bar that we have, we would have that is 237,875 minus 12 times 2,700 divided by 12 times 1037.8 divided by 12, and that will give us 4,370. So that's our sxy there, and I'll go on and write it on top there, just because I will need to use it. We now go on and calculate sxx. It's given by the formula there is summation of x squared minus n times x bar squared. And substituting the values that we have above there, we would have it as 645,000 minus 12 times 2,700 divided by 12 squared. And the result there will be 37,500. So I'll go on and write my sxx on top there, because I will need to use it later. So the sxx is 37,500. So we have our sxy, 4,370, the one that I've highlighted. Our sxx, we are saying, is 37,500. Our beta 1 hat, we are saying, is sxy divided by sxx. So if we substitute those highlighted values, we get 4,370 divided by 37,500. and that will be approximately 0.1165. So we have obtained our beta 1 hat there. So we now go on and calculate beta not hat. For beta not hat, we'll be looking at the y bar. The y bar there is 1037.8 divided by 12, then minus the beta 1 hat that we've just calculated. I'll use the number that is not rounded. This one here, we say it's 4,370 divided by 37,500. That's our beta 1 hat. And then you substitute the value of the x bar is 2,700 divided by 12. So substituting that into the formula for beta naught hat, which is on the right there, it will give us the 1037.8 divided by 12 minus 4,370 divided by 37,500 multiplied by the x bar, which we are saying is 2,700 divided by 12. And when you simplify, that gives us 60.2633. So we have that our beta naught hat is approximately 60.2633. So in this case, our fitted model there will be yi hat approximate 60.2633 plus 0.165 times xi. So that will be the estimate of the yi. I now move on to the next stage of the ANOVA table. For the ANOVA table, we need the summation of y squared. And from your calculator, from the values that you would have entered, you will get that the summation of y squared is 90,265.52. And we'll then go on and calculate the sum of squares total. The sum of squares total is the summation of y squared minus n times y bar squared. And then using the values which are above for the summation of y squared and the y bar, we have that is 90,265.52 minus 12 times 1037.8 divided by 12 squared. And that will be approximately 513.1167. So that's our sum of squares total. For the sum of squares regression, and the formula there is beta 1 hat times sxy. And the xy we have it there, we have already calculated it. And the beta 1 hat we have it there is 4,370 divided by 37,500. Our sxy we have it there is 4,370. So when I substitute those values, we get our sum of squares regression is 4,370 divided by 37,500 times 4,370. And that will be approximately 509.2507. So that's our sum of squares regression. I now go on and look at the sum of squares error. The sum of squares error is sum of squares total minus sum of squares regression. And when we use the sum of squares total that we have there, and the sum of squares regression that we've just calculated, we have our sum of squares error is 513.1167 minus 509.2507, which will give us 3.866. So that's the sum of squares error. So I'll just write the values that we need there, the n, the sum of squares total, the sum of squares error, the sum of squares regression. Then go on and write the ANOVA table. So I'll draw a table there. We have the source, the degrees of freedom, the sum of squares, the mean square, the f there. So we'll be looking at the regression and the error, then the total. At the regression degrees of freedom, we are given them the is 1 there. So the degrees of freedom for the regression is a 1. And the degrees of freedom for the error is n minus 2. In this case, our n, we are saying is a 12. So it will be 12 minus 2, which gives us a 10. So the degrees of freedom error there is a 10. Then we go on to the total degrees of freedom is n minus 1, which will be 12 minus 1, which gives us an 11. Or you just add the regression TF and the error TF there, 10 plus 1, which gives us an 11. Our sum of squares regression, we have it there, 509.2507. So I'll put it in the table there, 509.2507. Then the next one, the sum of squares error, we have it there, 3.866. So I'll put it in the table there, 3.866. Then the sum of squares total is 513.1167. I'll write it in the table there, 513.1167. So I'll now go on and calculate the mean square regression. The mean square regression there is a sum of squares regression divided by 1, which gives us 509.2507. So I'll write the mean square regression there is 509.2507. I now go on and calculate the mean square error. The mean square error is sum of squares error divided by the degrees of freedom, the 10, and it gives us 0.3866. For the F there, the F is the mean square regression divided by the mean square error, which is 509.2507 divided by 0.3866, which gives us 1317.25. So I'll go on and write our F there is 1317.25. The next step is to look at the statistical tables of the F, which is the degree of freedom D1 being a 1, the D2 being a 10, our alpha is a 0.05, and from the tables we see that the F there is 4.96. So in this case what we see there is the calculated F, the 1317, is greater than the one from the tables there. So since the calculated F is greater than the one from the tables there, we reject the null hypothesis and conclude that the regression is significant. I now go on to the last part, the hypothesis testing. We have our H naught, beta naught equals to 0 versus the alternative beta naught not equals to 0. When we are looking at the intercept beta naught, the test statistic is given by beta naught yet minus A divided by S times the square root of 1 divided by N plus X bar squared divided by SXX. Our beta naught yet, we calculated it, it is 60.2633. Our A is a 0, N, the observations, we are having a 12. The mean square error there gives us the sample variance. So we have our S squared is 0.3866. And when we have the sample variance to get the standard deviation, the S, we take the square root. So we have our S there, the standard deviation is 0.3866, square root of that. Our SXX, we had calculated it and we saw it was 37,500. Our X bar is 225. So when we plug in those values, we get that our T there is 80.9559. We reject H naught if the calculated T, its absolute value, is greater than the one from the tables, that is degrees of freedom N minus 2, and the level of significance alpha divided by 2. But in this case, we are saying our N is 12, so we'll be looking at degrees of freedom 10 from statistical tables. For the T with degrees of freedom 10, the level of significance 0.05 divided by 2, it gives us a 2.23. So what we'll be having there is that the calculated T is greater than the one from the tables. Therefore, we would reject H naught. The H naught there, we are saying we are rejecting that beta naught is equal to 0. What we are concluding there is that the intercept is significantly different from 0.